Hello, everybody. In this video, we're going to discuss what are the goals and the topics of this class, kind of a very, very high-level overview of what we're going to do in this class. So this class is about formal models of computation, formalizing what computations are, and with these notions, theory is not about formalizing things just for the sake of formality, but we are formalizing, so we have the language and tools to ask questions that are important. And here the question that we're going to ask is, what is computation? What can be cast and understood as a computation? What can and cannot be computed? And finally, what can and cannot be efficiently computed? Because if something can be computed using resources that are unavailable, more time than the time that this universe exists, more memory than the number of atoms in the universe, then knowing that it can be computed is not very, very meaningful. So we're asking what can be computed efficiently, and at times even what can be computed practically, which is a somewhat different question. The answer for these questions relate to various areas: philosophy, mathematics, engineering, and as I hinted in the previous video, also to the sciences, including the social sciences. What are the goals of this class? What do I want you to get out of this class? I want you to know some of the basic principles in the theory of computing, and I want you to know them at different levels of understanding. So some of them I just want you to be aware of, and some of them I want you to be able to do something with. I want you to be able to formalize and prove some properties of computation, some central properties of computation. And also to be able to apply some of the principles of computational thinking. And one example, perhaps the most important example, I want you to understand reductions very well. Turns out to be a very powerful notion. Some of us, including myself, can think reductions to a large part of our careers. And I want you to get some exposure to some of the areas of theory in hope that you will continue to further explore theory beyond this class, and even if not, at least so you're aware that some of these things exist. So for quite a few of you, surprisingly, this course is not mandatory, and still you choose to be here, which I'm very, very grateful for. And the question is why to take theory beyond what you're forced to do. And I want to claim that theory is good for you. Indeed, in some cases, although theory is kind of this very, very abstract and partial model of the world, and the world is so powerful, there have been quite a few examples where this theory led practice. In cryptography, many of the things that existed first through purely theoretical ideas that it's hard to imagine them being developed outside of theory. Quantum computing is another example. This notion of quantum computing developed in theory way before we had any hope of developing quantum computers, and even now, quantum computers are still not there. And that's not true only for quantum computation, for any digital computers. These models of computation and the theory of what computation can do existed before digital computers existed, so started to exist before digital computers exist. And to be fair, there are other areas, for example, deep learning, where practice has just gone very quickly, and theory is kind of trying to catch up. But usually, eventually, when we catch up, we're still able to shed some interesting light. And I think that deep learning is one case where we're starting to see important insights coming from theory, although theory didn't lead the charge. On a more practical level, some of you at some point may try to implement things, and being able to understand what can be computed and what cannot be computed is an important ability. Otherwise, you're trying to devise algorithms that are impossible. And if the problems we want to deal with are impossible, then the question is, okay, what other things are possible? What kind of approximation of what we want to do is possible? In addition, theory gives you lots of tools, and these tools are just useful, like we talked about, like reductions, for example. It's useful ways of thinking about problems. And finally, and perhaps this is a huge emphasis of this course, theory and the power of theory is often about being able to model questions in the right level of abstraction such that it's abstract enough that we can analyze it, but it's real enough so what we get in return can have a real impact. And I can say personally that I've spent time in both academic and industrial environment, and often my contribution to collaborations, let's say in industry, wasn't some specific area of expertise that I brought, but it was the ability to formalize and abstract things that was really, really very useful, to view them kind of in a much clearer way. So this is part of what having lots of theory help you do. So let's talk about models. This is a model of dancing, or a primitive model of dancing, but it's not the only model of dancing. All of those model dancing, and each one of them has a different impact. So this, for example, allow you to write to write down dancing, and this is a picture of an amazing dance. And this is a photo that perhaps brings some of the emotions that are there in the dancing. So why do we need so many models? We need them exactly because of that. Each model, and similarly for computation, each models allow us to understand another aspect of computation. For example, a different way in which a resource of computation has an impact, whether this resource is memory or randomness, and computation under different limitations. So the different models that we'll see will help us understand different aspects of computation. And finally, I want you to get out of this class some basic understanding of some basic concept. So kind of imagine a very nerdish cocktail party. I want you to be prepared for it. Prepared to discuss the Gödel incompleteness theorem in a couple of intelligent sentences, to talk about the Church-Turing thesis or the complexity theoretic Church-Turing thesis, to understand something about quantum computations, and to have some experience with PCPs. Not these PCPs, sorry. What I mean is probabilistically checkable proofs, which are, again, a very powerful concept that I invite you to understand. So let's see what's the map of what we're going to do. And we can think that very roughly we have 3 chapters to this class. The first chapter will talk about finite automata, which is a notion that's pretty old, from the 40s and 50s. And indeed, some new classes about the introduction of computation are kind of retiring finite automata, but I feel that talking about finite automata is still useful. And it's useful because it's a very simple model. Essentially, this is a model computation that has fixed, constant amount of memory. Through that, because of its simplicity, it will allow us to characterize what can be computed and cannot be computed in this model. So we'll be able to make very strong statements about computations. We'll also have the first encounter with non-determinism, the power of guessing. We'll be able to argue what cannot be computed. And we'll be able to talk about optimization and to talk about learning in this context. The learning part will be just a taste. And finally, we can talk about things that are very modern and very important perspective on finite automata, which is streaming algorithms, and which is the more algorithmic aspect, and communication complexity, which is the more complexity theoretic aspect. It allows you to talk about, it will allow us to argue about streaming algorithms and what can be done by finite automata. The second chapter will be about computability. Again, a very old notion, a very old theory. And here, we will talk about a very powerful model. So unlike the finite automata, Turing machines are very powerful, and we will talk even about computations that are even more powerful than Turing machines. And still in this model, we can talk about what cannot be computed at all in this model, what's undecidable or not recognizable. And the way we'll show that there are some things that cannot be will be by first giving the first kind of foot in the door problem, example of things that cannot be computed in this model. And then we'll get many more problems that cannot be computed through reductions. So as I said, reductions are a very important aspect in this class. And if one hard problem or a family of hard problems is not enough, we'll actually mention an hierarchy of exceedingly hard problems. So for every problem that cannot be computed in some sense, we'll find a problem that cannot be computed in an even stronger sense. So this will be the hierarchy of exceedingly harder problems. We'll take these insights as a way to also discuss the foundations of mathematics through the lens of computation, and their development and development of some of the very basic models of computation is highly related to logic and the foundations of mathematics, and we'll give you some taste of this connection. And we'll talk about Kolmogorov complexity, which will be a kind of a universal theory of information in a similar way to the fact that Turing machines is kind of a universal theory of computation. Finally, we'll get to the third chapter that's much closer to current time research, which is complexity theory, a topic that's very close to my heart. And it's already old topic, but it's continuing to be developed all the time, although many of the things that we will see are old results. We'll talk about time complexity, about the notion of P versus NP, about NP completeness. We'll have another return of non-determinism. This is the NP, the notion of NP will highlight that, but here it will play a much stronger role, a much more important role. So we'll examine non-determinism, the power of verified guessing again. And similarly to the story for computability, we'll start with our foot at the door, which is the one problem that is likely to be hard to compute, which is, we'll talk about satisfiability. So a problem that is likely to be hard. It can be computed, but probably not efficiently, not in any reasonable amount of time. And again, we will get many more problems through this notion of reductions. Now it will be a refined notion of reductions. polynomial time reductions. And again, we will have an hierarchy of hard problems. All of the hard problems that we'll discuss here are problems that can be computed, but they cannot be efficiently computed, or likely cannot be computed efficiently. And for every problem that cannot be computed efficiently, probably we'll find one that's probably harder, even if that one could be computed efficiently. We'll mention in much less detail other resources of computation: space, randomness, communication. We will not discuss other resources that are becoming more and more important, like power. And we'll give another kind of visit to the computational length, crypto, game theory. So I don't want to leave you just with this kind of very big list. I want to give you one example of something we'll care about. And this is the notion of map coloring. So here is a problem, a computational problem. You're given a map. And given a map, you want to color it because you want to be able to separate the different states very easily, the different countries. So a legal coloring is one where a country is not bordering another country with the same color. And bordering is more than just a corner. So it doesn't have a real border against a country that is that has the same color. The question is, can you legally color this with 3 colors? Turns out that there is a famous theorem, the 4-coloring theorem. It's mainly famous because it was partially proven with the aid of a computer. So the proof included parts that were not done manually by humans, but by a computer. But all of these maps can be colored by 4 colors. Now the question is, can you color it with 3 colors? I'm not even asking you for the exact coloring, but just whether you can color it by 3 colors. So this looks like one, and perhaps a toy problem out of infinite amount of computational thing we would like to do. But let me argue that this is the central, or perhaps the most foundational question in computer science, and one of the central questions of math. And if you were here with me, I would take a poll and ask you, do you believe me or not at this point? And history shows that many don't believe me that this is such an important problem. And let me argue that it is so important because this is one way in which you can state the P versus NP problem. So whether or not you can find an efficient algorithm for this one simple to understand and almost kind of a toy problem, if you can find an efficient algorithm for this, then P equals NP, and if not, then P is different than NP. And we'll understand much more why and how something so innocent looking can be so important when we'll discuss P versus NP in the 3rd chapter of the class. Thank you.